Okay, so I want to do a quick little lesson on, law of large numbers versus central limit theorem. Fight. So the idea here is that the weak law of large numbers gives us kind of a bound on how quickly I expect things to converge to the mean, but it's not actually using the underlying true PDF of anything, right? It's kind of using the Chebyshev approximation, which we already know is conservative. Whereas a central limit theorem, if I'm summing up a bunch of random variables, I can be much more confident that the sum of those random variables looks like this Gaussian at the end of the day. So let me just do an example. Let's suppose that I roll a fair die 20 times and count the number of total dots. And I want to know what is the probability that the sum of the dots is in the range 60 to 80. Okay, so there are a couple ways that I could go about this problem. Okay, so first of all, let's just realize that each of the x's, right? Each of the xi's is uniform on 1 through 6, right? So my mean for the random variable is the basically the middle number, which is 3.5, and my sigma I can look up in the table is basically 6 squared minus 1 over 12, which is 35 over 12. Actually, that's the variance. So this number is about 2.92. So my actual sigma is the square root of this, which is about 1.71. Okay, so all this is kind of like preliminary. So what would the law of large numbers tell me about this thing? So the weak law of large numbers version will say the following. The probability that the sum of the dots, so the sum of 20 things, and here I'm going to kind of rewrite this as saying that I'm plus or minus 10 from 70. Right? And again, what is my expected value? I do 20 rolls, and the average is 3.5. So my expected value of those 20 rolls is 70. So I've chosen an interval that is centered about the mean already. Well, this is the same as I'm going to divide through to talk about the mean of these 20 numbers being within this value. I'm sorry, not 3.5, divided by 20, right? So a different way of saying this is this. Okay, so what would the weak law of large numbers tell me, right? It would tell me that this is at least equal to 1 minus sigma squared over n epsilon squared, right? So in my case, this is going to be sigma squared we found was 2.92, n was 20, epsilon here is 1/2. So I can do the math, and it turns out this is equal to 5/12, which is approximately 0.42. Okay, so this is telling me that the odds are okay that I'm within 10 of the true mean. Okay, now the different way of doing it would be to say, hey, after I do 20 examples, the sum of these things is really close to a Gaussian. So I should be able to get a very precise number, a very precise estimate for the probability. So the central limit theorem would say the probability that this mean minus this number is less than or equal to 1/2, right, would be equal to 1 minus 2q of z, where this z here is z sigma over square root of n equals 1/2. So again, I have to go back and think about what do I know, what don't I know. I don't know z, right? So it's like saying that my sigma is 1.71. My n is 20. So I can do my computation and I can find out that z is equal to 1.31. So my more accurate bound would be 2 times q 1.31, and then I go back to my table and I find out that this is like 1 over 2 times, I can read it off as approximately 0.0968. This answer turns out to be 0.81 approximately. So Here, this is actually much more, it's certainly higher than this thing I got before, right? So this is like saying that probability has to be at least 0.42. Turns out it's a lot more than 0.42. It's more like 0.8, right? And I can trust this number more because it comes from the fact that after I add up these 20 numbers, this is very close to being Gaussian, right? Remember that things converge to that bell curve. And so I could be much more confident that this number was right than just saying, well, it's at least 0.4. So that's a handy thing to think about, is that when you're talking about lots of random numbers aggregated together, the central limit theorem is generally going to be much, much more accurate.